we stand forever at a point in time called now. The past, we can only remember. At best, we can learn from it. The future, we can only surmise. At best, we can try to shape it. Less than 5 hours from this point of now, John A. Mankey will find himself suspended 8 miles above the Mojave Desert. As test pilot for NASA's Flight Research Center, he will play out his role in shaping the future in a wingless craft that looks as though it has no right to fly. 3 hours now. John Mankey has already flown an F-104 over the test range to check for turbulence and returned satisfied. In the nearby physiological van, a medical team is affixing tiny sensing devices to his body to transmit his physiological reactions during the flight to recorders at ground control. Since weeks before now, engineers and technicians have been checking and rechecking every fitting and instrument and connector in this lifting body called the HL-10. Finally, to fill its tanks with the alcohol and liquid oxygen that will, in little more than 2 hours, propel it for the first time faster than the speed of sound. Getting men into space is one problem. Getting them back is another one. They ride out on thundering names like Mercury and Gemini and Apollo, batter their way back through the searing atmosphere at more than 17,000 miles per hour. And once through that barrier, ride parachutes to an ocean splashdown. For infrequent missions, a widespread recovery force of dozens of ships spread over hundreds of miles can be justified. But as more and more men are suited up to leave their world, as flights to and from orbiting space stations become more frequent, then easier, more flexible, less costly ways to let them return simply must be found. That's what John Mankey and the HL-10 and NASA and the Air Force are doing, making sure answers will be ready by the time they're needed. Less than 90 minutes from now, the flat-bodied craft will be carried 8 miles high beneath the wing of this B-52, there to be released as another step in the proof of a theory conceived almost 20 years ago at NASA's Ames Research Center. Up to the present, manned spacecraft have been cone-shaped, re-entering blunt end first, but they lack maneuverability. At first, it might seem reasonable to turn the vehicle around and re-enter with the pointed end forward. However, this shape would generate excessive heat, and more important, it still would not have the desired maneuverability. The first modification was to make its cone slender and blunt its nose, but it still could not fly well or be maneuvered. So the next modification was to slice the cone lengthwise. In effect, this reduces the pressure on the top, so that pressure on the bottom will dominate, providing more aerodynamic lift and greatly reducing drag. In theory, it should fly, but could it be maneuvered and landed? Ideally, a way was needed to bring down the half cone much like a conventional airplane. For such a landing, the best shape is shallow and broad. By flattening and widening the half cone and adding aerodynamic surfaces for control, a configuration was evolved, a lifting body capable both of high-speed re-entry and low-speed landing. Such a craft could act as a shuttle, carrying people and material from space stations back to Earth. From outer space, its pilot could maneuver it to touch down at a pre-selected landing site, or, if necessary, alter his course and land at a different location. Unlike the now familiar space capsule, the lifting body is reusable. Its initial cost could be spread over hundreds of flights, and the configuration lends itself to larger sizes, able to carry dozens, perhaps scores of passengers. But a child must crawl before he walks, and walk before he runs. In the lifting body program, crawling for John Mankey means countless hours in this simulator, up to 50 hours for each flight, while an analog computer interprets his every move and patiently plots out the reaction it would produce if he were airborne. And it means many dead stick landings in an F-104, trimmed to approximate the lifting body's characteristics. Seven years earlier, the first full-scale flight test model crawled, literally, as an automobile towed it aloft at the end of a cable. Simple in construction and low in cost, it nevertheless did what the wind tunnel tests had said it would. It flew. Now it was time to walk. The DC-3 towed the lightweight steel and plywood lifting body and its pilot to altitudes up to 12,000 feet. There it was released and allowed to glide in free flight to the desert floor, to land at a speed of 80 miles per hour. This first test vehicle logged over 400 successful flights. But all that is the past for John Mankey. As with fellow test pilot Bill Dana, who will control this flight, he walks toward his future, less than 90 minutes from now, poised beneath the protective wing of the B-52. Mankey is a professional, long familiar with flight test procedure. That procedure is to increase the performance step by step until the craft has been pushed to its limits in terms of altitude and speed. Lifting bodies have flown before, of course, and many times. The first heavyweight configuration was called the M2F2. On a hot July day in 1966, another NASA test pilot, Milt Thompson, made the first glide flight. Even though developed from the earlier configuration, this was no plywood lightweight, but a fully equipped test vehicle weighing almost 3 tons and designed to touch down at over 200 miles per hour. The 8-mile drop took less than 4 minutes. One successful flight proved only that it could be done. Refinements, improvements, the evolution of an idea into a working system would have to come from many such flights. From hypersonic wind tunnel evaluations, and from constructing and testing a number of different designs. This lifting body, the HL-10, with 3 vertical stabilizers instead of 2, was developed at Langley Research Center. Less than 6 months after the initial M2F2 flight, the HL-10 took its first plunge to the desert, with NASA's Bruce Peterson at the controls. Then, shortly after launch, trouble. Problems with the controls. Next, a strange high-speed buffeting the wind tunnel tests had failed to disclose. Peterson could have ejected, but he still had control of his craft and chose to ride it out as the ground reached up for him at more than 200 miles per hour. like what pilots would call a piece of cake. It always does after someone has done it and the moment has been frozen on film. Can John Mankey, now less than an hour from takeoff, put from his mind another moment? A long moment that began a year before when Bruce Peterson again dropped away from the mothership in the M2F2. A moment that continued as violent oscillations suddenly struck the craft near the ground. The pilot managed to recover, but too much precious time and altitude had been lost. The moment ended. Miraculously, the man survived. So did the airframe, to be rebuilt for future flights. But for John Mankey, this is now. Sealed in his own tiny world, he has too much ahead of him to reflect on the past. He knows the control problems have long been corrected. And in 45 minutes, and what will be only its fourth rocket-powered flight, he will push the HL-10 through the sound barrier of Mach 1, up to 724 miles per hour. The lifting body has proved over and over that it can maneuver and land, but wind tunnel tests have never shown exactly what will happen as it exceeds the speed of sound. Only when its rocket engines kick it through that critical barrier will they and John Mankey be sure. The test will be labeled a success, though of course he can't know that yet. To the scientists whose speculation made it conceivable, to the engineers and technicians who made it possible, to John Mankey, whose life depends on all of them and his own skill besides, this is the successful completion of another milestone. But in a broader sense, it is just a test. Another step in the evolution of an idea. Future flights will go higher, up to the fringe of the atmosphere, and return at speeds well above the speed of sound. In the now that will be with us tomorrow, a lifting body may return men and women from space, much as commercial jets land today. Or from this work, some new, as yet unthought of configuration may emerge. For the moment always with us called now, always changes.
January 31st, 1977, the Mojave Desert. Space Shuttle Orbiter 101 is being transported from its assembly facility in Palmdale, California, 35 miles overland to NASA's Dryden Flight Research Center at Edwards Air Force Base. This orbiter, named Enterprise, is the first of a fleet of reusable space transports. Like nothing ever before built, the shuttle orbiter is a hybrid, part spacecraft, part airplane. Upon returning from space, the orbiter, with no air-breathing engines, will be flown to a powerless landing like a glider. Now, performance and reliability must be proven in the approach and landing tests of the Orbiter Enterprise. For testing, the 75-ton spacecraft will be carried atop a 747 jumbo jet to an altitude of about 5 miles, then released by firing a set of explosive bolts. The test will be carried out in 3 stages: the captive inert phase with no orbiter crew aboard, then the captive active, and the free flight stages, both with astronaut crews at the orbiter controls. Taxi runs begin the captive inert testing, in which the orbiter stays atop the carrier aircraft, and none of the orbiter's systems are turned on. The big 747 is maneuvered along the runway at speeds up to 157 miles an hour to determine steering, braking, and ground handling characteristics while carrying the orbiter. Next, a series of 6 captive inert flights is scheduled, still with the orbiter unmanned and its systems inactive. 747 Captain Fitz Fulton and co-pilot Tom McMurtry will fly the carrier aircraft as chase planes help monitor the operation. Their mission is to obtain information on performance of the mated vehicles. The crew is pleased. Handling is much closer to that of a standard 747 than expected. Subsequent captive inert flights check for stability and control problems and accomplish flutter tests. Flutter is a term for high-frequency oscillation, which can build up in aircraft parts, causing structural failure. The orbiter's position atop the carrier aircraft changes the normal airflow around the 747 tail, reducing stability and causing tail buffet. For this reason, special fins, resembling outriggers, have been added to the horizontal stabilizer to restore directional stability. A tail cone fitted to the orbiter and covering its 3 main engines allows it to be carried higher while reducing 747 tail buffeting. After separation, since the tail cone also reduces air drag on the orbiter, it will be able to descend more slowly, allowing more time for testing in flight. A tail cone will also be used to reduce tail buffet on ferry flights when the 747 transports orbiters from California to the launch facility in Florida. But for space missions, the orbiter's engines will be left exposed, and the vehicle will re-enter the atmosphere and land without a tail cone. The captive inert flights continue with technical evaluations. Emergency descent is simulated. Finally, all procedures up to the point of actual release of the orbiter are carried out. The testing goes so well that flight number 6 is not required. The captive active phase can begin with the orbiter crew aboard and the orbiter systems active. Astronaut crews have been training for the approach and landing tests. A shuttle training aircraft, or STA, is constructed by modifying a Gulfstream II airplane to handle like an orbiter. Inside, the left seat and controls are changed. Computer equipment is added. In the STA, a crew practices landings. Spacecraft Commander Fred Hayes and spacecraft pilot Gordon Fullerton. Briefings are held on orbiter systems with another crew, Spacecraft Commander Joe Engel and spacecraft pilot Dick Truly. At the Johnson Space Center in Houston, Texas, a computer-controlled trainer, the Orbiter Aeroflight Simulator, or OAS, is used to practice landings. Orbiter crews operate the controls, causing a special television camera to scan a scale model of the dry lake bed on which the orbiter will land at Edwards Air Force Base. The result, a realistic orbiter landing, is seen through the simulator windows.
Gear coming.
the crews are well prepared. Astronauts Hayes and Fullerton will fly the first captive active test, alternating the missions with Engel and Truly. The control room at Dryden Flight Research Center manages operations before the flight and maintains contact with the carrier aircraft. It will also serve as a contingency control room in case communication should be lost with the control center in Houston. The control center is the Recovery Operations Control Room at Johnson Space Center, the same control room used for recovery operations during the Apollo program. The orbiter's fuel cells are active now, furnishing 15,000 watts of electricity for coolant systems, communication equipment, and flight control systems, including the 5 onboard computers. 4 of these computers are redundant, working together as a set, comparing information when asked to make a decision. If failures occur, normal operation can still continue with as few as 2 of them functioning. Finally, the crew can fly the orbiter using the 5th computer only if the redundant set fails. Other power is furnished by special hydraulic turbines called auxiliary power units, or APUs. They supply energy for mechanical functions, such as moving the flight control surfaces. It is during these captive active flights that problems occur with the power units. A sensor shows excessive temperature in the APU system, but a later check reveals that it was accidentally triggered by a loose wire. The wire is replaced. Another power unit problem surfaces. A seal in a bellows unit is leaking, allowing APU fuel to drain overboard. The bellows, already being redesigned, is replaced by a modified unit, and the system is safe. 3 captive active flights are made so that problems like these can be discovered and corrected. The last captive active flight includes a full rehearsal for the separation maneuver. The 747 crew pushes over and accelerates the mated pair to 310 miles an hour. They are descending at 3,000 feet per minute. The orbiter's elevons and ailerons are positioned to provide the correct angle and lift for the actual release, the next phase of the approach and landing tests. Astronauts Fred Hayes and Gordon Fullerton will man the Enterprise for its first free flight. Of the scheduled series of free flights, 2 are considered the most critical. This flight and a later one for which the turbulence-reducing tail cone will be removed. Free Flight 1 will test the separation, the handling qualities of the orbiter, and certain systems will be evaluated, including braking and steering during rollout. Now the 747 is near the altitude required for the pushover maneuver. The crew of the orbiter Enterprise is completing its pre-flight checklist. Due to buffeting, the ship vibrates, causing the astronauts' voices to shake.
We're in 202. CSS. CSS, they're steady. Surface is steady. Okay, I'm all set to push over. Get the cameras at the wideband and then the arm at 240. Okay, Enterprise is set. Thanks for the left, Fitz.
905 and Enterprise, Houston is go for pushover.
905. Coming to launch heading.
Houston copies.
2, 1, pushover.
Houston copies pushover.
The carrier aircraft has pushed over and acceleration begins. The orbiter pilot will arm a series of explosive bolts, and when separation speed is reached, the commander will fire the bolts, releasing the orbiter. An orbiter pitch-up maneuver will provide vertical separation, and the 747 will turn left, while the orbiter turns right for horizontal separation. Then the crew of the Enterprise will be on their own, flying to an unpowered landing on the dry lake bed.
220, 235, 240, mark. Arm, no lights, 2 lights. Okay, we are armed, 2 lights, and the orbiters go. 250.
Houston is go for SEP, have a great flight.
And we'll stand by for the bang, Gordo. Power. Stand by. It wasn't too bad. Now.
At separation, computer number 2 stops processing data. The other general processing computers, or GPCs, in the redundant system voted off the line. The crew informs the control center, executes the planned computer malfunction procedures, and Free Flight 1 continues.
Okay, pitch up.
Clear up. Got a
Okay, we
mass
got
alarm.
a computer light. It's number 2.
Okay, we got a GPC light, loss of sync on 2, pushing over.
And a big X on computer number 2.
Roger, we understand.
Roger. Okay, I guess, yeah.
Okay, she's flying good. 250, starting flare.
Okay, your AA breakers are coming out. And we're going to get a message.
Yeah, that's a definite lurch.
Sideways lurch, just like they said. Okay,
Okay, 11 Alpha, pushing over.
Okay, I got you 195 and 20,000.
You got it, Gordo.
I got the airplane.
Okay, straight.
Okay.
Enterprise, you're cleared to start to turn.
Okay, Gordo's in the turn. It is really tight, Bo. In fact, I think it's a little better than the OLS TA fields.
Yeah. The lurch is there, just like everybody said. Okay. Altitude's on, and I'm about 14 lower than you are in speed and right on altitude.
The orbiter is not controlled like a standard airplane. The onboard computer system, using information provided by flight sensing devices, makes constant adjustments to the control surfaces so that a stable attitude is maintained. When the pilot moves the control stick, the signal goes first to the computer system. The computers instantly adjust the control surfaces so that while the pilot's command is obeyed, stable flight is maintained. If the weather is bad and visibility poor, the orbiter can be flown in an autoland mode. In autoland, the orbiter is brought to a landing by the computer, which determines its location, direction, and speed through its inertial guidance system, its microwave landing system, and other data sources.
Got a steady auto land, 900. Arm,
Okay, we're armed and flaring.
standing by the gear.
200 feet, 290.
Okay, the gear is coming down at 270. Coming down.
Mark.
Gear coming.
Doors open and they're all down. Some are down. What's down here? 50
Okay,
feet.
3 downs. Gear's down.
40
240. 230.
20.
220, lots of speed.
10.
Beautiful.
Holding 10.
210.
220 at about 5 feet.
210.
4 feet. Getting some dust.
200.
3 feet. 2 feet.
195.
Just overlaps about 2 feet.
185.
You're on. You're on.
Okay, speed brakes. Speed
Hey,
brakes
you're
are
gonna be
coming.
about 10 feet.
Speed brakes are halfway out.
Drop. We'll see you, babe.
Okay, I got 130 knots.
Okay, it's great.
120.
Low rudder.
115. Okay, 80. Okay, 60 knots. Try the nose wheel.
Okay, that was too good a glider.
Free flight time, 5 minutes and 22 seconds. Roll out with moderate braking, a little over 2 miles.
It's a lot better than the OAS. Look at that.
Free flights 2 and 3 have furnished additional engineering data. Required adjustments have been made to Orbiter 101 systems. Now, astronauts Joe Engel and Dick Truly will make free flight number 4, the first flight with the tail cone off.
Start out, of course.
When an orbiter returns from space, it will not carry a tail cone. This will cause increased turbulence behind the craft and will create more air drag. During this critical flight with the tail cone off, the tail section of the 747 will receive even greater punishment from the turbulence. But if all goes well, the 150,000-pound Enterprise will be released and will descend 20,000 feet in 2.5 minutes. First, the mated vehicles are checked in flight with the orbiter's tail cone off. A data run is made to monitor performance at separation speed. Then the 747 begins its climb for pushover and actual separation.
Smoothly. Enterprise has 2 lights. We're go for SEP.
Roger, Enterprise. Houston is go for SEP. Go for SEP.
Okay, Dick, let's do it pretty.
210 knots. 220 knots. 230 knots. Stand by for launch ready, Joe.
Okay. SEP. Okay. Coming up.
Body flap set.
Good. Okay, pushing over.
Okay. Okay, Joe, we're configured. Beautiful. 190 knots.
Free Flight 4 is going well. Instrumentation and power systems are performing normally. Carrier aircraft buffeting was within the established limits before separation. And during free flight, the orbiter's handling qualities are not noticeably different than they were with the tail cone on.
285 knots, you're looking good. 290 knots, 4,000 feet. 3,000 feet, 290. You're a little fast, Joe.
Leave them out.
Pre-flare.
You're on the glide slope. We see you on the glide slope.
Want the speed brakes coming in?
Negative. Leave them. Okay, now start them in.
Okay, they're coming in. Speed brakes closing.
Orbiter gear.
Okay.
Get the gear.
Gear's coming. Okay, 200 feet, Joe, 260 knots.
Down.
Good. 250 knots. 240 knots. 230 knots.
10 feet.
220 knots.
5 feet.
210 knots. 200 knots. 190 knots.
Down.
Speed brakes are tracking.
Nose is coming down. 2 feet. 1 foot. Down.
Brakes.
Back up. Nose wheel steering on. Off. Differential braking. Your brakes, Dick.
Okay, I've got the brakes.
Push them hard.
Okay.
Okay.
Okay, let me get a little slower here, Joe. Okay, I'm coming off the brakes.
Okay.
I'm on the right brake.
Okay, I'm coming in slow. Come on, brake. I'm holding what I got.
Okay. Okay, Houston, we're stopped. Mark.
Roger, got it.
Look good
Thank you,
from
Bob.
here.
Thank you, Richard. That was a super one.
Free flight time, 2 minutes and 35 seconds. Rollout with hard braking, 5,275 feet. The orbiter flies well with the tail cone off. On this flight, Free Flight 5, the orbiter will land on a paved runway. The performance of the landing gear and its connected airframe systems must be verified on this type of surface. Also, the orbiter's approach, landing, and rollout will be tested on the paved strip with a simulated 10,000-foot length. The Kennedy Space Center runway, where the orbiter will normally land as it returns from space, is 15,000 feet, and the additional 5,000 feet will mean a greater margin of safety. Free Flight 5 goes well until just before touchdown. Then a pilot-induced movement takes the vehicle close to the ground. It rises. At 187 knots, it touches down, but skips off the ground and settles 1,900 feet later to a second touchdown. The total runway rollout distance from the first touchdown point is 7,930 feet, well under the 10,000-foot mark. With Free Flight 5, the approach and landing tests are concluded. All of the assigned program requirements have been satisfactorily completed. Now Orbiter 101 will go to Marshall Space Flight Center in Alabama for a series of ground vibration tests. In 1979, the 747 will carry Orbiter 102, sister ship of the Enterprise, to Kennedy Space Center in Florida, where it will be the first vehicle to be used in the orbital flight tests. Each shuttle orbiter is designed to be used at least 100 times. The Space Shuttle fleet will handle a variety of missions: placing, servicing, or recovering satellites in orbit, delivering deep space probes for on-orbit launch, carrying space laboratories. NASA's Space Transportation System will replace nearly all expendable launch vehicles for both civilian and military space missions. With the shuttle orbiters, we're entering a new era in space.
In the early days of our republic, Americans watched Yankee clippers glide across the many oceans of the world, manned by proud and energetic individuals, showing our flag, breaking records for time and distance, opening up new vistas of commerce and communications. Well, today, I think you have helped recreate the anticipation and excitement felt in those home ports as those gallant ships were spotted on the horizon heading in after a long voyage. The fourth landing of the Columbia is the historical equivalent to the driving of the Golden Spike, which completed the first transcontinental railroad. It marks our entrance into a new era. The test flights are over. The groundwork has been laid. And now we will move forward to capitalize on the tremendous potential offered by the ultimate frontier of space.
When thousands of civilians began pouring onto a military base, located on a desert, in the middle of summer, early on a Sunday morning, one could sense the day's events were going to be special. Spectators came to Edwards Air Force Base from all over the nation and all walks of life to celebrate the nation's 206th anniversary of independence and witness historical events more spectacular than the typical 4th of July fireworks display could ever hope to equal. The fourth landing of Space Shuttle Columbia, world's first reusable spacecraft. Columbia's first landing on a concrete runway, officially ending the orbital flight test program. Takeoff of the second orbiter in the shuttle fleet, Challenger, on its ferry flight to Kennedy Space Center, Florida, to be launched into space in the early part of 1983. And with Shuttle Pathfinder Enterprise as backdrop, the announcement of America's new space policy by President Ronald Reagan.
Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security. Simultaneously, we must look aggressively to the future by demonstrating the potential of the shuttle and establishing a more permanent presence in space. Our goals for space are ambitious yet achievable. We've only peered over the edge of our accomplishments.
Surely, our accomplishments began with Columbia's first launch in April 1981.
We have main engine start. Back barrel program. Go. Roger, roll. Roll program complete. Roger, roll complete.
Looking back at that spectacular event and the performance of Space Shuttle during its first 4 flights, there seems little doubt now that it is a reliable, reusable space transportation system. When Columbia first arrived at Kennedy Space Center in March of 1979, there was some skepticism. 2 factors were leading to major delays in the launch schedule.
The quest to advance the state-of-the-art in space technology, particularly in engine design and thermal protection, plus budgetary limitations imposed on development and testing of shuttle systems. With 2/3 of shuttle's tiles already on the vehicle, it was discovered that the bond was not strong enough to keep the tiles from falling off during high-stress phases of flight. The fix, called densification, required that most of the tiles be taken off, coated with a material to increase the bonding strength, then reapplied to the vehicle. The process took over 1 year to complete, but it worked. During the orbital flight test program, only undensified tiles showed weakness along their attach points on non-critical areas of the vehicle. Shuttle's main engines achieved the state-of-the-art in rocket engine technology. But as with any research and development program, confidence in the design came only after years of testing, learning, and some mistakes. Problems encountered during development of the engines were related to the unique requirements that had to be met. Reusability, up to 55 flights with minimum maintenance, ability to throttle down to 65%, lightweight, yet the capability to withstand extremely high chamber pressure, pressure needed to generate the thrust for liftoff. Many failures that occurred were due to the tremendous pressures and vibration levels created trying to produce the needed thrust. But one by one, the problems were solved. The design was proven long before the first launch.
Brake is closed. 5, 4, we've gone for main engine start. We have
Columbia was launched. Again. And again. And again. Four times within 15 months, traveling over 8 million miles during the first 4 flights. "314 revolutions around the Earth. 19 days on orbit." But beyond the statistics, a far more important goal was achieved with completion of the orbital flight test program. The foundation for our future was built, step by step, mission by mission. The goal of STS-1 was, quite simply, to get up and get down safely.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your goal for on orbit.
When astronauts John Young and Robert Crippen heard that announcement, they knew the mission was at least half a success. When returning from space, friction created by entering Earth's atmosphere blocks communication between mission control and the astronauts for 15 to 20 minutes. But it is also precisely during that time that temperatures on the vehicle surface reach their peak and shuttle structure undergoes its most stringent test. On Columbia's first flight, no one could predict exactly how shuttle would perform during that phase.
Hello,
Hello, Columbia, Houston's here. How do you read? And we're doing Mach 10.
With voice contact reestablished, spacecraft and crew had safely passed through the most critical phase of entry. Landing was the final test. Flown as a glider, Columbia landed without power on the first and only attempt.
They're coming. Go down. 50 feet. 40, 30, 20, 10, 5, 3, 2, 1, touchdown. There's gear, 10 feet. 5, 4, 3, touchdown. Houston, Columbia's on the roll. Welcome home, Columbia. Beautiful, beautiful.
Columbia's second flight was the first opportunity to evaluate the Canadian-built remote manipulator system. Manual functions were tested by astronauts Joe Engel and Richard Truly. Automatic functions were computer-controlled. The arm performed successfully in all operating modes. Preliminary thermal tests of the vehicle were also begun on Flight 2. One thermal attitude resulted in the payload bay being pointed toward Earth for extended periods of time. During those periods, a package of 5 Earth-viewing instruments, designated OSTA-1, was activated. The package, composed of low-cost commercial-grade sensors previously flown only on aircraft, and instruments flown on individual satellites or past manned missions, collected the first Earth resource data using Shuttle. The ability to mount all 3 types on Columbia greatly reduced the expense of acquiring the data.
Okay. 100, 50, 30, 20, 10, 5, 3, touchdown. Nose gear 15. 10, 5, 3, touchdown. Welcome home. Thank you, Chase.
Flight 2 proved Shuttle was truly a reusable space transportation system. Third flight of Columbia was primarily a thermal test of the vehicle, exposing it to the most extreme temperature differentials it could encounter on orbit during upcoming operational flights. No facility on Earth could simulate the same heating conditions Columbia would experience in the vacuum of space, where temperatures could vary greatly from one end of the orbiter to the other, depending on its orientation to the sun. The thermal tests determined precisely what effect different attitudes had on shuttle structure. The vehicle suffered no adverse effects. Evaluation of the remote manipulator system continued on Flight 3. Astronauts Jack Lausma and Gordon Fullerton tested the system's payload handling capability. First order of business was unberthing. Although clearance around the payload was only 2 inches, Fullerton unberthed in just 5 minutes, much quicker than had been predicted pre-flight. Using the plasma diagnostics package, 7 computer-controlled automatic movements of the arm were evaluated to prove scientific instruments could be maneuvered in and around the payload bay.
Only some general comments on the arm operation. The operation is smooth. There's definitely a little bit of flex and dynamics, but in the augmented modes, that's very minimized. really no surprises. If there are any surprises, they're all pleasant. I'm really impressed with that piece of machinery.
Hey, that's great news, and we were impressed too.
The plasma diagnostic package was one of 10 instruments making up a scientific package on Flight 3 called OSS-1. Shuttle's movement through the ionosphere, electrical buildup on surfaces as it circled Earth, and electromagnetic interference between the ionosphere and electronic equipment on board were evaluated by the OSS-1 instruments to ensure that these phenomena would not adversely affect scientific instruments or sensitive astronomy observations on future shuttle flights. On Flight 4, the Induced Environment Contamination Monitor was used to check for contamination in and around the payload bay, created by thruster firings, outgassings, and water dumps. 11 separate components of Shuttle's induced environment were measured. The desk-sized monitor was the heaviest payload lifted by the remote manipulator system during the orbital flight test program. Thermal tests on the vehicle were completed during Flight 4. The first Department of Defense payload was on board. The spacesuit to be used for extravehicular activity on Flight 5 was tried on during Flight 4 to practice the procedure. And astronauts T.K. Mattingly and Henry Hartsfield conducted a thorough evaluation of on-orbit procedures for the upcoming operational era of spaceflight, when Columbia will launch into Earth orbit on a routine basis. An ongoing task on all 4 missions of the flight test program was to evaluate living conditions on board shuttle. Items included food preparation, use of a food warmer, a freezer on board Flight 4, and eating in weightlessness. Personal hygiene tasks were evaluated. As were sleeping conditions, use of sleep restraints, and a sleeping bag. Astronauts also evaluated the effects of exercise in zero-G. This unique device, designed by a fellow astronaut, allowed the user to monitor his own heartbeat while jogging. Alternate methods of anchoring oneself in weightlessness were also appraised. Very busy schedules are forecast for upcoming shuttle flights, when crews will be comprised of at least 4 people, including women. procedures on the ground are being streamlined for the operational era. Processing time was cut in half during the orbital flight test program. Presently, it takes approximately 13 weeks to prepare the space transportation system for launch. It is projected that by the mid-'80s, there will be 2 shuttle launches per month. The number of people in mission control is gradually being reduced. Some positions have been eliminated. Others have been consolidated, which represents a clear indication of confidence in Columbia's systems. While this monitoring is being streamlined, payload monitoring is increasing. A new area called the Payload Operations Control Center was activated during the orbital flight test program to give mission controllers, payload managers, and commercial users the opportunity to develop monitoring and data acquisition procedures for upcoming flights. Experiments in life sciences were carried on board Columbia during the orbital flight test program. A preliminary study of lignin growth in zero-G was conducted. Lignin is an indigestible skeletal substance which promotes strength and upward growth in woody plants. It is hoped that in the absence of gravity, woody plants might not need to produce as much lignin, and instead will produce more digestible nutrients, such as carbohydrates and protein. The effect of weightlessness on some flying insects, bees, moths, and flies, was studied. The project, conceived by a high school student, was one of 3 experiments flown on Columbia as part of an annual science competition co-sponsored by NASA and the National Science Teachers Association. Equipment to process materials in zero gravity on future flights underwent initial testing during the orbital flight test program. The monodisperse latex reactor made polystyrene latex microspheres to determine if large identical-sized latex microspheres could be manufactured practically and economically in space. Presently, large microspheres cannot be produced in uniform sizes on the ground. Yet medical and industrial applications have already been found in cancer research and treatment, glaucoma research, and for calibration standards in medical and scientific equipment. The continuous flow electrophoresis system, built by McDonnell Douglas Corporation, is a prototype of a production unit to purify material for the treatment of disease. The process separates substances according to their electrical charge. Hopefully, yields from the production unit will be high enough to make the product available to a mass market in the future. Results from the prototype's first flight showed that a very thin, yet highly concentrated stream of protein substance on the left was separated from red dye on the right. The thin protein stream, only a portion of which is shown here, is actually over 43 inches long and is 300 to 400 times more concentrated than yields obtained from the same process on Earth. The continuous flow electrophoresis system represents the first commercial use of shuttle by private enterprise under a joint endeavor agreement between NASA, McDonnell Douglas Corporation, and Ortho Pharmaceuticals Corporation, a subsidiary of Johnson & Johnson. A unique opportunity to put small, self-contained payloads aboard shuttle on a space-available basis at a very low cost exists in the Getaway Special program. After proving its flight readiness on Flight 3, the Getaway Special was fitted with 10 experiments built by science students from Utah State University and flown on Flight 4. Deposits for Getaway Specials on future flights, private enterprises' interest in flying payloads on board shuttle, missions planned into the next decade, all reflect the confidence this nation has in the space transportation system. All objectives of the flight test program were achieved. Two of the most significant events were not planned. Just prior to the third launch, tons of landing and recovery equipment had to be transported from California to New Mexico, a 1,000-mile journey, because heavy rains in California prevented a landing there. An entire encampment had to be built at the New Mexico landing site, Northrop Strip, and the task had to be completed within 4 days. Just prior to landing on the same mission, only 1.5 hours before touchdown, an unexpected sandstorm blew into the area.
As you could probably surmise, the winds have been coming up all day. It was still acceptable until his last pass, but during John's last pass, the visibilities were unacceptable and the turbulence was severe. So it's not a good day, and we're going to wave off for 24 hours. Over.
Plans were implemented immediately to stay on orbit an extra 24 hours.
We've had a good drill.
The flexibility to remain on orbit until weather conditions improved and land at an alternate strip could not have been demonstrated by previous spacecraft. Only the shuttle has that capability. It meets a need, providing access to low Earth orbit on a routine basis. By launching on time, serving as a platform for Earth observation and space observation, deploying payloads, operating in extreme temperature differentials while on orbit, providing ample living accommodations for astronaut crews, landing on lake beds, or concrete runways. As President Reagan said, the end of the orbital flight test program marks our entrance into a new era. The test flights are over. The groundwork has been laid. Now we will move forward to capitalize on the tremendous potential offered by the ultimate frontier of space.
Okay, and the port restraint is out. Here comes the spin. Here it goes.
Yeah, we see it down here, Bill. It's beautiful.
Okay, Mike, we're at 52, coming back down 51 RPM.
Roger, we copy. You guys look good. And Columbia, Houston, everyone down here is go for deploy with 2 minutes left over Hawaii.
And so is everyone up here.
Roger, we copy.
Mike, we hope the TV comes out. It doesn't play back very well on a monitor, but we're relatively sure we got it. And we, by the way, still have that beautiful satellite inside. It's traveling just below it.
Roger, we copy, Bill and Joe, and got a lot of happy people down here. You guys did good work.
Okay, Mike, we delivered. We got SBS off on time. And if you're interested, I'll read you the pad.
Roger, go ahead.
Deliver the crew of Shuttle Mission 5 did. Only 8 hours into the first operational flight of the Space Shuttle program. 5th flight of the orbiter Columbia. The first 4 missions were test flights to prove the space transportation system could provide access to low Earth orbit on a routine basis. Those missions laid the groundwork for the operational era. Shuttle Flight 5 was the beginning of that era. The primary purpose of the mission, to carry 2 communication satellites into orbit, deploy them from the payload bay, then return to Earth.
Columbia, Houston, 30 seconds till LOS, and everything is still go down here for deploy.
Roger, Brian, we copy that. Thank you very much. We're looking forward to having a good one.
Roger, and good luck.
Okay, Houston, this is Columbia. We are 2 for 2. We deliver. Hey, Roy, are we down now? That was, are we on the ground?
Absolutely.
A flawless landing. Only minutes after sunrise at Edwards Air Force Base, California, ended Columbia's 5th mission. Looking slightly weathered, the orbiter had traveled over 10.5 million miles in 5 flights, spent 24 days on orbit, and circled the Earth almost 400 times. It would now return to Kennedy Space Center, Florida for refurbishment, to be launched again on Shuttle Flight 9. The newest orbiter in NASA's fleet, Challenger, would fly on Shuttle Flight 6. Many weight-saving improvements had been made. The orbiter itself was almost 2,500 pounds lighter because of structural changes. The external tank weighed 10,000 pounds less than the one used on Shuttle Flight 1. The solid rocket boosters were almost 4,000 pounds lighter. The 3 main engines were upgraded to 104% of rated thrust. A blanket-like thermal material replaced 600 thermal tiles in non-critical areas, and all 30,000 tiles were densified to improve their durability. This stack could carry over 17,000 pounds more into orbit than Columbia.
Minus 15, 14, 13, 12, 11, 10. We'll go for main engine ignition. 7, 6. We have main engine ignition. And liftoff. Liftoff of the orbiter Challenger and the 6th flight of the Space Shuttle. The shuttle has cleared the tower.
Challenger's underway. We got a whole program.
Houston copies, Challenger.
And some late news for your story. We got a go for deploy. We have a go for deploy.
On Shuttle Flight 6, Challenger's cargo, the tracking and data relay satellite, TDRS, and its solid propellant inertial upper stage rocket, the IUS, weighed almost 19 tons. TDRS was the largest, most advanced communication satellite launched to date.
That is correct.
A major accomplishment in space communications. TDRS is launched from the payload bay by ejection springs, released when explosive bolts are fired. After shuttle moves a safe distance away, the first stage of the IUS rocket fires to boost the satellite from 150 miles to 22,300 miles in altitude. Then the first stage separates. Shortly thereafter, the second stage of the IUS rocket fires to circularize the satellite's orbit. Solar panels and antennas are deployed to provide power and tracking and data relay capability. Having attained a circularized altitude of 22,300 miles and traveling at the same speed as the Earth's rotation, the satellite will remain fixed in orbit over the same location continuously. Later, the first TDRS will be joined by two more identical satellites. The three will form a space communications network, providing almost continuous coverage to Earth-orbiting spacecraft, not the 15% ground stations provide. The network will be able to track 26 Earth-orbiting spacecraft simultaneously. And because TDRS satellites only relay data, they do not process it, 20 times more information will be handled by this network than could be by ground stations. All data will be relayed directly to the primary NASA ground terminal, White Sands, New Mexico, and from there via domestic satellite to other NASA centers.
Hello there, we're with you.
Launch of TDRS was on time and nominal. First stage firing of the inertial upper stage also went well.
And Sunnyvale and White Sands send you a special attaboy.
However, halfway through the second stage firing, ground controllers lost communication with the satellite. It was an hour before even intermittent signals were picked up. They indicated TDRS had not yet separated from the IUS, and that both were tumbling at a very high rate of speed. Receiving only intermittent signals from TDRS, using short-life batteries which would soon be depleted, and getting no response to signals sent from the ground, made the outlook for TDRS bleak. Several more hours passed, and then something remarkable happened. Experts still aren't sure why, but either an automatic timing mechanism was engaged, or onboard systems finally acknowledged repeated commands from the ground, separating TDRS from the IUS.
Well, I do have some words.
Now on its own, the satellite stopped tumbling. Ground controllers commanded deployment of the solar array and antennas. However, they quickly learned TDRS was way off course and drifting farther every day. Their only hope of getting it back on course was to use the tiny hydrazine thrusters originally designed for minor attitude and velocity adjustments, not for boosting the 2.5-ton TDRS over 8,500 miles farther into space. But at least the satellite was not lost. NASA officials immediately put their plan into effect. Meanwhile, Shuttle Flight 6 continued as planned.
Okay, we're back with you, Milo, for about 12 more minutes. Got a good TV picture again.
Roger, Houston. Got the hatch closed, and we're waiting for a go for depress on time.
That sounds great, Bo.
Copy, we have a go for depress on time.
That's affirmative, you have a go. And Challenger, Houston's with you over Guam for about 7.5 minutes.
Roger, hatch is open. EV1 is halfway out. They're configuring the airlock, getting ready for dawn to come out.
Okay, we're watching.
Houston, they have a suggested setting for the DAC camera now in the sunlight. Okay, dawn.
This was America's first spacewalk in 9 years. The astronauts were attached by safety tethers to slide wires running just inside the payload bay. They wore a new design in spacesuits, also called extravehicular mobility units. A portable life support system was worn on the back, eliminating the need for a lifeline connected to the orbiter. These suits are not custom built for each astronaut. Tops and bottoms of different sizes can be mixed. They are also more flexible than previous spacesuits. The crew removed tools from a storage locker in the front part of the payload bay. Then moved aft again. Using a cable run through a winch mounted on the bulkhead, then tied to the cradle that had held the IUS, the astronauts demonstrated they could have lowered the cradle manually had commands from on board failed. Winch operations were tested on the front bulkhead using an exergenie as a load to see how many pounds the winch and line could handle. Lastly, the tools were re-stowed, and the astronauts re-entered the spacecraft.
Indian Ocean for 2.5.
Perhaps the most visually spectacular mission since America's first landing on the moon, Shuttle Flight 7 gave us our first glimpse of the orbiter from a distance.
Another space first.
John, we have had one more of those intermittent dropouts, but the spas came right back up and no other problems.
Thank you.
The magnificent views were provided by a European payload called SPAS.
We copy?
SPAS is an acronym for Shuttle Pallet Satellite, a unique, reusable space platform built by the West German aerospace company Messerschmitt Balkov Blom, with generous financial assistance from the West German Federal Ministry of Research and Technology. In addition to having American television and film cameras mounted on SPAS, 10 experiments belonging to the West German government, the European Space Agency, and NASA were on the platform. MBB wanted to validate the satellite's design and prove experiments could be operated while SPAS was free flying. NASA wanted to show the remote manipulator system could handle the 2.5-ton payload.
And TJ, we just turned on the mass spec to warm it up. I assume that you wanted us to do that.
Affirmative, Sally. Thank you.
Okay, TJ, we're with you, and John performed a beautiful release.
Wonderful, wonderful.
The orbiter's ability to station keep with SPAS was also demonstrated. At this point, they are 1,000 feet apart. Here, SPAS and Challenger are 200 feet apart. Thrusters on board the orbiter were fired to record the effect on SPAS. SPAS was rebirthed for return to Earth.
I've been told that some crews in the past have announced that we deliver. Well, from Flight 7, we pick up and deliver.
We certainly hope so.
The remark by Shuttle Flight 7's commander meant not only had the SPAS operation been successful, but that the crew also deployed 2 communication satellites. A Canadian satellite to be used for one of the world's first direct-to-home pay TV services, and an Indonesian satellite. It would increase high-speed data transmission and telecommunication service to that country's remote island locations.
Roger, the weather at KSC is getting worse instead of getting better, so it looks like we're a no-go for KSC.
Shuttle Flight 7 was to be the first landing of an orbiter at Kennedy Space Center, Florida. But bad weather conditions did not allow it. Challenger would touch down instead at Edwards Air Force Base, California, the alternate landing site.
Roger.
During the period of communications blackout, usually lasting about 15 minutes, temperatures on the vehicle's surface reach their peak. The temperature of the red-hot glow seen through Challenger's front windows was about 2,400 degrees Fahrenheit. One astronaut described the view as like being inside a furnace.
Processing Western test range data.
Houston, Challenger, loud and clear. Nice and smooth all the way down.
Real good, Crip.
Been running about 5 to 7 tenths aileron trim on the right.
Roger, we see that.
I'll say once more, we're away to come to California.
Roger that. Challenger, Houston, rolling on off the hack. Your energy looks good. Surface wind 180 at 10.
Houston, Challenger is will stop.
Roger, we see that. Congratulations, a great looking landing.
Roger that.
Approximately 2 months after TDRS was first launched from Shuttle's cargo bay on Flight 6, the final firing needed to place the satellite in its correct orbit was executed.
Copy. Go ahead for the burns.
Personnel began immediately to check out communication systems on board and initiate a series of important ground tests with the satellite essential to its operation on upcoming shuttle flights.
Processing TDRS.
First use of TDRS with Shuttle was on Mission 8.
Challenger, Houston with you on TDRS.
Houston, Challenger, loud and clear. How do you read a CDR?
Roger, loud and clear also.
Challenger, this is Houston with you through Hawaii for 7
Also
minutes.
conducted on Shuttle Flight 8 was checkout of the remote manipulator system and payload flight test article.
You're loud and clear too, Dale, and looks like you're right on schedule.
The 8,500-pound structure was the heaviest object lifted by the arm to date, more than double the weight of any previous payload. Data gathered during the checkout was used to plan the Solar Max repair mission. On that flight, a 20,000-pound payload would be deployed, and an orbiting satellite would be retrieved.
At 0008.
We're ready to deploy.
That's good news.
Flight 8 marked the 6th successful launch of a satellite by Shuttle. It was an Indian communications satellite which would bring telecommunications, television, and badly needed weather information to remote areas of that country. Because Challenger was launched at night on Shuttle Flight 8, parts of the southern hemisphere never seen or photographed from space were visible during daylight hours. The first night landing for the Space Shuttle program occurred on Mission 8 with safe touchdown of Challenger at Edwards Air Force Base, California. After making its first voyage into space on Shuttle Flight 4, the Continuous Flow Electrophoresis System, CEPHAS, flew again on shuttle flights 6, 7, and 8. The device is a prototype of a production unit to purify material for the treatment of disease. It was built by McDonnell Douglas Corporation and flown on shuttle as part of a joint agreement between NASA, McDonnell Douglas Corporation, and Ortho Pharmaceuticals Corporation, a subsidiary of Johnson & Johnson.
Challenger, Houston.
Combined results from Flights 6 and 7 demonstrated that Cephas could separate over 700 times more material, and in purities 4 times higher than could be achieved in Earth's gravity. Shuttle Flight 8 was the first use of Cephas to separate living cells. Some of the samples were separated to continue research at Pennsylvania State University and Johnson Space Center, Texas. The McDonnell Douglas samples were used to further diabetes research at Washington University Medical School, Missouri. Other scientific activity conducted on shuttle flights 5 through 8 also focused, as the Cephas had, on research and materials processing, greatly enhanced when performed in the weightlessness of space. The monodisperse latex reactor flown on shuttle flights 3 and 4 flew again on missions 6 and 7 in a continuing attempt to improve the production of polystyrene latex microspheres for cancer research and treatment and glaucoma research. 5 student experiments flew on the 4 shuttle flights as part of an annual science competition co-sponsored by NASA and the National Science Teachers Association. Studies ranged from fluid convection to sponge and crystal growth to biofeedback. A total of 23 getaway special canisters were flown on shuttle flights 5, 6, 7, and 8. Some contained stamped envelopes from the U.S. Post Office commemorating spaceflight. Others grew snow, exposed seeds to zero gravity, and studied the effects of weightlessness on a colony of ants. NASA's Getaway Special program is a unique opportunity to fly small, self-contained payloads onboard shuttle on a space-available basis at a very low cost. Perhaps the studies with the most human interest were those done on space adaptation syndrome, also known as space motion sickness, a malady which affects approximately half of all astronauts. The most extensive studies of SAS were done on Flight 8, focusing primarily on the neurological system. Oral sensitivity was tested, eye movements, and repeated physical motion. Measurements were taken of limb volume and external tissue pressure. If any of these tests looked torturous, it's no wonder the crew dubbed the doctor's mid-deck working area a chamber of horrors, and mockingly gave him a taste of his own medicine. Astronaut crews got along exceedingly well with each other on missions 5, 6, 7, and 8. Yet they were the largest, most diverse crews in the history of spaceflight. Flight 5 carried the first 4-person crew. Flight 6, calling themselves the Over-the-Hill Gang, tallied up all their years of experience to get this grand total. Flight 7 carried the first 5-person crew, including the first American woman to fly in space, Sally Ride. Flight 8 included the first black American to fly in space, Guyanne Bluford. And the oldest person to fly in space to date, Dr. William Thornton. With ejection seats gone from the flight deck, and water storage tanks and instrumentation gone from the mid-deck, there was much more room to accommodate the larger crews. There was also opportunity for privacy, exercise, and as usual on any important trip, plenty of food. The success of Flights 5, 6, 7, and 8 represented many accomplishments for the Space Shuttle program. More importantly, the missions proved the operational capability of the space transportation system, that useful work can be done in space for the benefit of people on Earth. But the program has really just begun. Third orbiter in the shuttle fleet, Discovery, will be launched in 1984. The fourth orbiter, Atlantis, will be ready for use in 1985. New astronauts are being recruited. 73 shuttle flights are scheduled through 1988. The outlook for the future of America's space shuttle program is excellent, and there appears to be no end in sight.
The space station, another step in the continual building process, where each venture into space forms the foundation for exploring the universe. As man strives to reach new heights in space exploration, he must first develop the skills necessary to successfully live and work in the zero gravity of space. The year is 1973. America's first home in space, Skylab, is in orbit. Throughout the 3 Skylab missions, flight crews conducted a variety of experiments in medicine, Earth observation, engineering, solar physics, and astrophysics. The technology developed during Skylab provided the basis for the design and development of future long-duration space stations. In addition to providing a laboratory for important studies, Skylab marked a significant transition in the spaceflight program. In each Skylab mission, we became workers rather than observers. Skylab also provided a testing ground for techniques and equipment which would be needed for man to work effectively in space. One of the tools tested, the astronaut maneuvering unit, would prove its usefulness on future flights of the Space Shuttle. February 1984, the 11th mission of the Space Shuttle program, Mission 41B, is in orbit.
4 miles a second, Bruce.
The astronaut maneuvering unit tested on Skylab is now called the Manned Maneuvering Unit, or MMU. Its first checkout in space is about to begin.
Okay, here we go. Well, that may have been one small step for Neil, but it's a heck of a big leap for me.
Copy that, Bruce. Thank you.
Oh, this is really beautiful out here.
Here, McCandless was 300 feet out from the spacecraft. He had proven the manned maneuvering unit could be flown in space, and he simulated something very important. He traveled the same distance another astronaut would have to travel 2 months later. to get from shuttle to an ailing NASA satellite.
204 feet.
On the next shuttle flight, the satellite called Solar Max would be picked up by the shuttle, repaired on orbit in the payload bay, then returned to space.
Marvelous machine.
Solar Max was launched from Kennedy Space Center, Florida on Valentine's Day, 1980, in the year of the solar maximum, the 1 year out of every 11 that the sun is most active. But within 9 months, Solar Max had developed serious problems.
The Solar Max repair mission was a very interesting experience from a number of points of view. For some number of years, a team of people at the Goddard Space Flight Center had championed the idea of designing satellites so that they could be repaired on orbit or retrieved and brought back to Earth for repair. It was a chance to demonstrate the kind of things that both the Goddard people who designed the satellite and we who operate the STS had been saying, that is, that we can do these things on orbit. Satellites that are designed to be repaired on orbit can save a great deal of money because we don't have to bring them back, we don't have to launch them again. Building things so that they can be fixed is going to become a byword of the satellite and space station design of the future.
In fact, one of the main reasons for the 41B mission was to test the tools and techniques that would be used to repair Solar Max on the next flight.
The plan to capture, repair, and re-release the Solar Maximum spacecraft had been over 2 years in the making. One of the essential elements of this plan was to use the maneuvering unit and this device mounted on the front, known as the T-pad or trunnion pin attachment device, to capture an existing hardpoint on the Solar Maximum spacecraft and to stabilize it for RMS retrieval and repair. In order to lessen the mission risk to the subsequent mission, 41C, we were assigned the task of conducting an MMU test flight and of proving out the trunnion pin attachment device function on our flight. In addition to the activities with the manned maneuvering unit on STS-41B, we had another important piece of equipment to evaluate for the first time, the manipulator foot restraint. The manipulator foot restraint is analogous to the cherry picker that construction and power line crews use, and is basically a foot platform with ski boot-like bindings that you can lock your feet into, that mounts on the end of the remote manipulator arm and can be positioned anywhere in the cargo bay area and holds you in a firm, stable position without expending propellant, as the MMU is required to do, for hours at a time. The manipulator foot restraint carried tool boards equipped with tools such as this modified power tool. On the backside, additional simple hand tools. And I exercised this against a mock-up of the electronics unit and some of the other detailed mechanical tasks that were to be performed by Ox Van Hoften and Pinky Nelson on the subsequent STS-41C flight.
Challenger Houston, at this time, West Star is go for deploy.
Roger, we'll go for deploy.
Unfortunately, Flight 41B was also the mission on which the West Star and Palapa communications satellites failed to reach their expected orbits. The deployment of both satellites from Shuttle's payload bay went off without a hitch, but the rocket motor nozzles failed, causing the thrust to be dispersed. Without propulsion, the satellites could not reach transfer orbits.
So we had to explain the difference in what the NASA responsibility was and how the part of the mission during which we had this failure and the equipment that was represented in that failure was really the responsibility of the communications satellite customers that we were flying. NASA provides the shuttle ride, and the customers design, build, and pay for their own satellites and upper stages, somewhat independent of NASA.
April 1984, Shuttle Flight 41C on orbit, having rendezvoused with the Solar Max satellite.
Challenger Houston through Hawaii, and we've got a good picture of Pinky flying in the bay.
Copy that. I'm just doing a little, getting some hands-on time, Jerry.
Roger, copy that, and ground's giving you a go for the MMU flyover, and the POX commanding is inhibited until we're on the FSS and tilted.
There go, 1 potato, 2 potatoes.
Maneuvering unit pilot George Nelson made his way over to the satellite. Commander Robert Crippen, pilot Dick Scobie, and mission specialist Terry Hart monitored his progress and the progress of James Van Hoften, waiting in the payload bay. Nelson was having trouble docking with the satellite. The T-pad was not locking onto the trunnion pin, and his attempts were causing the satellite to wobble. His maneuvering unit propellant level was also getting low. He would have to return to the shuttle. Solar Max would have to be grappled instead with the shuttle's robot arm. Nelson headed back in while the crew on board prepared to capture Solar Max. The shuttle was out of range of voice and picture coverage, while Bob Crippen maneuvered the ship and Terry Hart tried grappling the satellite with the robot arm. On the ground, mission controllers anxiously awaited word from the crew. Minutes went by before they got the news. The grapple didn't work.
Of course, we were very disappointed we didn't get it. We'd been training for a year, and all of a sudden we were missing it. We ended up, after that 4th attempt that we made, and we still missed, and we were getting real low on fuel. That was when the ground told us they thought that they might be able to stabilize it from the ground. So we backed away and turned it over to the Goddard Space Flight Center in Greenbelt, Maryland. The main thing that we had a problem with was, since it was wobbling, it wasn't pointing the solar rays at the sun. Consequently, the electricity was going down and down and down.
Goddard immediately went to an alternate plan for restabilizing Solar Max. A new attitude control program was transmitted up to the satellite's onboard computer. To give as much power as possible to this new stabilizing attempt, Goddard turned off all the heaters, the instruments, and everything else not essential to the stabilizing effort. Solar Max was entering a crucial eclipse on the dark side of the Earth. When Solar Max emerged, its power was almost gone, but it had stabilized considerably. The method worked. The next time controllers checked, the satellite had stabilized even more and moved into a position that exposed the solar panels to the sun for a brief 10 minutes. When the crew awoke from their sleep period, Goddard had presented them with a Solar Max that was ready for capture. Crippen could now move the shuttle toward the satellite for another grapple attempt with the robot arm.
This is Mission Control, Houston. Loss of signal at the tracking satellite. The remote manipulator arm was in motion at the time of loss of signal.
Challenger Houston standing by through Yargady.
Okay, we've got it, and we're in the process of putting in the FSS.
Outstanding.
With Solar Max secure in shuttle's payload bay, the repair could now begin.
The first order of business, of course, was to change out the attitude control system. That was the main thing, to repair the satellite. Next, we attempted the main electronics box, which is a major part of one of the prime experiments. That night, the ground went through the checkout of the satellite to make sure that it was working properly.
Challenger Houston, your go for release as long as you're within 5 degrees.
Roger.
The next day, we redeployed the satellite with the attitude control system and all 7 of its experiments working properly.
The first retrieval and repair of a satellite in space had been a success.
The Solar Max repair mission was a great achievement. It was an example of planning to do something and finding that the primary method of doing it, that is Plan A, didn't work. We had to call upon Plan B during the course of that flight.
The fact that 41C was a success strongly influenced the decision to make 51A a mission which would rescue the Palapa and Westar satellites. An interesting aspect of this mission was that NASA did not own the satellites. The insurance underwriters owned them.
So what was new for us was that now we had a new party involved in the discussions, in that the ownership of the satellites was in fact the insurance underwriter in both cases. So we had a set of discussions in Washington, primarily at our headquarters level, where the details of working out the agreement as to who would pay for what and how much NASA would charge the underwriters gradually developed over a period of time.
A crew was named and began training as a team, with equipment designed and built specifically for the rescue of Palapa and West Star. Perhaps one of the most important elements of the retrieval operation was the Apogee Kick Motor Capture Device, or Stinger as it was called. It was the tool the astronaut would use, together with his maneuvering unit, to capture the satellite, stabilize it, and bring it back to the shuttle. Hughes Aircraft Company had to begin the complex job of maneuvering the satellites into position before final negotiations with the insurance carriers could be completed. Otherwise, there would not have been enough time to place Palapa and West Star in the precise position, in the precise orbit, at the precise time for rendezvous with the shuttle. On November 8, 1984, the shuttle and its crew of 5 set out to rescue Palapa and West Star. Palapa was there. Hughes Aircraft Company had lived up to its end of the bargain.
Holy mackerel. I am not 20 feet from that satellite.
Maneuvering unit pilot Joe Allen flew over to dock with Palapa, while Commander Rick Hauk, pilot Dave Walker, and mission specialist Anna Fisher monitored his progress and the progress of Dale Gardner, waiting in the payload bay. Allen inserted the Stinger device into the satellite, docked, then, using his maneuvering unit, stabilized the satellite. Fisher moved in with the robot arm
Get in there and grab that thing. Just go get it, Anna.
and brought Allen and the satellite back into the payload bay. There, Gardner attempted to attach the A-frame device to the satellite. The A-frame had a grapple fixture installed on it to be used by the robot arm to hold the satellite, while Gardner and Allen attached the support structure to it. The support structure was used to secure Palapa in the payload bay for its return to Earth. The shuttle went out of range of voice and picture coverage as Gardner attempted to attach the A-frame.
Houston, Discovery, we're going to let Dale talk. We got a problem here.
Discovery, Houston.
Okay, Jerry, here we go. The common bracket clamp will not fit on the satellite. The problem is, between the two octagons, between the two common bracket parts of the satellite, is a structure that's sticking out far enough that it is hitting the cross brace of the common bracket clamp, and it's not a piece of structure I can remove.
Okay, understand that, and what are you proposing to do?
We are proposing to go to the no A-frame procedure, and I will go up to the PFR in the forward pallet and try the technique perfected by yourself.
Okay, we copy Plan B and proceed.
Okay.
Plan B was a contingency procedure that astronauts Jerry Ross and Pinky Nelson came up with 1 week prior to launch. Unlike Solar Max, West Star and Palapa were not designed to be retrieved. The customers didn't intend ever to see these satellites again, so there was no need to pay for extensive documentation. As a result, mission planners had to anticipate that the drawings would not illustrate all the details.
So Joe, upon learning that indeed we're going to Plan B, had to detach himself and the backpack from the satellite, fly into the bay, stow the backpack, and come over and get into a foot restraint into a position such that he would now be able to hold the satellite with his hands. So the plan B that we chose was the one that required Joe then to take the place of the robot arm, to hold the satellite himself with his hands, while I performed the functions that needed to be done on the other end of the satellite. And then finally, when that was all done, for us together to berth the satellite into the payload bay, the other function that the robot arm would normally do.
Okay, yes, Joe, you can move across. If you got two, you can latch the third, guys. You ever ready back there?
3 latches down and locked.
Oh, my goodness.
Mission elapsed time 4:05:57:43.
All right, we got her.
The first satellite was secured in the payload bay, but it had not been an easy task. Perhaps Plan B could be improved upon. There was a one-day intermission between the Palapa and West Star retrievals, so Jerry Ross and Pinky Nelson went back into the water tank at the Johnson Space Center, where they first developed Plan B, to see if it could be improved upon.
But the major difference was I would hold the satellite from a position on the arm, the robot arm. And that enabled us to work in the vertical without getting near the satellite already safely stowed aboard.
Houston, Discovery.
Discovery, Houston.
Roger, we have 2 satellites latched in the bay.
Roger, that gave us a big cheer down here.
Mission 51A was a success, a dramatic example of the usefulness of man's presence in space. 51A also proved once again that plans and procedures could be altered on the spot if necessary to get the job done. NASA would put this experience into good use again in 1985 as 2 additional missions became involved in satellite rescue and repair.
Discovery, Houston.
April
You're looking good for
1985,
deploy.
Space Shuttle Discovery is in orbit. The mission started out normally enough with Telesat-1, a Canadian communications satellite, being spring ejected from the cargo bay.
Discovery, Houston.
During the crew's second day in space, SYNCOM-4 was deployed. Everything seemed to be going as planned.
2 for 2.
The crew watched expectantly for the omnidirectional antenna on top of the satellite to raise to its standing position. However,
Houston, this is Discovery. We are watching the SYNCOM. The Omni antenna is still down.
Roger, Ray. Any kind of visual assessment you can give of the SYNCOM spin up, etc., would be appreciated. We sure like any kind of good photos you can be taken at this time, too.
Yes, sir. The Omni is still down, and we're trying to watch the spin up.
Discovery,
about
Houston,
45 minutes after deployment from the cargo bay, the firing of SYNCOM's perigee kick motor, which would start the satellite on its way to geosynchronous orbit, did not occur.
Apparently, a switch lever on the side of the satellite didn't activate when it came out of the cargo bay. So the people on the ground began to search for a way to trip that switch. One thing they had to keep in mind was that anything that we used to actually trip the switch had to be constructed from materials that we already had on board. And what they came up with was a couple of homemade devices, and we called them the lacrosse stick and the fly swatter. And they were basically made out of some metal tubing, some plastic book covers that we had on our checklist, a metal window shade, also some wire and some gray tape that we carry on board on every flight. The devices were going to be attached to the end of the robot arm. The whole procedure for making and using these devices went through a trial run on the ground. They did runs in the weightless environment training facility where the spacesuit procedures are tested. They did some work in the arm training facility with a mock-up of the SYNCOM satellite to see actually what would work. The mission was extended for a couple of days so we could rendezvous with the satellite. And during that time, Mission Control sent up a massive amount of information on the teleprinter. That included detailed instructions for building the fly swatter and, in fact, an entire rendezvous checklist.
Mission specialists Jeff Hoffman and David Griggs prepared for the EVA, while mission specialist Ray Seddon maneuvered the robot arm into a convenient place for Hoffman and Griggs to attach the fly swatter devices to the end effector.
Howdy, we got a good picture of you. Jeff, I want to caution you that you're getting your pliss and maybe the helmet into the fly swatter there. You got to be careful that you don't get those things bent up.
Oh, okay, I'll try to move around. Easy, hold it, Jeff, don't do anything. Okay.
And Discovery Houston, you just got a round of applause. Thanks for the work.
Hey, you're welcome.
The next day, Commander Carol Bodko and pilot Don Williams maneuvered the shuttle into position for the rendezvous with SYNCOM.
I guess there was some question as to whether the arm could be used in this way. We were using some rather primitive tools on the end of the arm to see if we could tug on a separation switch and activate a satellite. We counted at least 3 really good whacks at it, but then the window of time in which correct activation was possible ended. Since we'd made hard contact with the switch, we had to back off from it in case the booster rocket was going to fire. The Omni antenna never did come up, but NASA decided that further attempts would not be made to try and trip the switch.
On the ground, Hughes Aircraft Company engineers performed an extensive failure analysis during the weeks that followed Mission 51D. This analysis led to the development of 2 separate electronics units designed to activate the dormant satellite. In the months following Mission 51D, NASA and Hughes agreed to develop plans for a shuttle mission to attempt to salvage SYNCOM. This joint effort was based largely on experience gained by NASA during the Solar Max repair mission and the retrieval of Palapa and Westar.
1, ignition, and liftoff. Liftoff of Space 51.
On August 27, 1985, Space Shuttle Mission 51I was launched. Among the objectives of this mission was to capture and repair the ailing SYNCOM satellite. On Flight Day 2, maneuvers to rendezvous with SYNCOM began. Once rendezvous operations were completed, the salvage and repair process could begin. Mission specialists James Ox Van Hoften and Bill Fisher prepared for the repair in the cargo bay, while mission specialist Mike Lounge operated the robot arm. And Commander Joe Engel and pilot Richard Covey monitored their progress. Bill Fisher describes the operation.
Ox secured himself in the foot restraints that were located on the end of the robot arm and was then moved into position to grab the satellite. Once Ox had gained manual control of the satellite, he was able to move it simply by pushing and turning it. At the controls of the robot arm, Mike carefully maneuvered Ox with the satellite in hand down toward me in the payload bay. I went to work repairing the satellite. This included some rewiring and also the installation of some electronics boxes, which would enable us to deploy the Omni antenna and also to establish communication between the satellite and Hughes ground control.
Okay, Omni deploy, fire. Omni, fire. Here she comes. Looking good. Looking good, buddy. All right. Bye-bye.
This is Mission Control. Today's extravehicular activity lasted 7 hours and 8 minutes. This broke the previous record by 1 minute.
The repairs required for SYNCOM were time-consuming, and 2 EVAs were required to complete the job. On the second EVA, we installed a new Perigee kick motor cover, removed the safe and arming pins, and set the timers on the electronics box that would eventually allow Hughes ground control to communicate with the satellite. We then installed a spin-up bar for Ox. On the end of the robot arm, Ox used the spin-up bar to position the satellite and then gave it a push to start the necessary rotations.
Okay, we copy. That's great work, everybody.
I can still see the timers blinking. I hope it works. Yeah, I do too.
The mission had been a success. Once again, NASA had demonstrated the skills necessary to efficiently work in space.
And I think we're going to find in the future that the whole concept of repairing things and maintaining them is just going to become a gradually more and more accepted idea that will make the space program just that much more robust and that much more inexpensive. It will cut some of the expense in the space program.
Experiences gained on Skylab and these Space Shuttle missions are the foundation on which space station operations of the future will be built. With the combination of a manned base and automated systems, the servicing of satellites will become routine, as will the deployment and operation of scientific instrument platforms. Capabilities not yet dreamed of, a future within our reach, as we continue to build towards new heights.